Hello everyone, this is going to be a short lecture on molecular polarity. And before we talk about molecular polarity, we are going to quickly revisit valence shell electron pair repulsion theory, or VSEPR theory, we call it for convenience, as well as trends in electronegativity of atoms across a periodic table. And we will talk about bond polarity as well, because the combination of these three factors determine whether molecules would be polar or nonpolar. So for valence shell electron pair repulsion theory, if you remember that we talked about the central atom being the most important, and the central atom and the electron groups around the central atom basically determines what the molecular shape would be. And the electron groups can be bonding electrons or non-bonding or lone pairs of electrons, as we call it. And the bonding electrons can be single bond, double bond, and triple bond as well. So once again, the central atom and the electron groups around it basically determines the shape of the molecule. So for bonding pairs or lone pairs or non-bonding electrons, we know that they actually repel the surrounding bonding electrons more strongly. And as a result, in this case, as you can see, uh, uh, these lone these lone pair electrons basically repel the SN-Cl bond much more strongly, causing it to have an angle of 95 degree instead of 120 degree, for example. We would expect a trigonal planar shape. For double bonds, we have instead of a single bond, if you have double bonds, you have more bonding electrons. Once again, that would cause stronger repulsion, and that's why we see this angle, instead of being 120 degrees, it's 122 degrees, slightly bigger, and it compresses or pushes away the CH bonds more. So instead of this bond being 120 degrees, it's 116 degrees. So we covered all that before. Then we talked about electronic shape versus molecular shape. So when we try to determine or try to describe the electronic shape of a molecule, we look at all the different electron groups, bonding or non-bonding. But when it comes to molecular shape, we only consider the bonding electrons to determine the molecular shape. And we use this formula where A is the central atom and X is the surrounding atoms, and X sub M is the number of basically surrounding atoms that we have, and E is represents the lone pairs of electrons, and then N basically how many lone pairs you have. So we have several cases that we covered. If you have two electron groups around the central atom, what happens? It's typically a linear shape, just like this, as you can see, because there are no lone pairs of electrons, so then there is no repulsion, and that's why you would expect the molecular shape as well as the electronic shape to be linear. For trigonal planar, or a central atom having three different electron groups, there are a couple of cases that you will encounter. First, if you have the same type of side atoms, surrounding atoms or side atoms, let's call it side atoms, around the central atom, then there are no lone pairs of electrons, and that's why it does not cause any kind of repulsion, extra repulsion. As a result, it has a nice triangular shape. We call it trigonal planar shape. So for example, we have boron trifluoride, sulfur trioxide, and other examples are here. But if you have something like one lone pair of electron right here, and then two bonding pairs, it takes the shape of a V. So we call it a Bender V shape. Water is a classic example of that, H2O. So due to the repulsion from the lone pairs of electrons, we see a Bender V shape. And remember, both of these have the same electronic geometry, electronic shape, which is trigonal planar. However, the molecular shapes are different. This one is trigonal planar versus this one is Bender V shaped, because in this case, the second case, we only consider the atoms. We do not consider the lone pair when we are describing the molecular shape, and that's the norm. So for four electron groups around the central atom, we have several options. So we have once again tetrahedral shape. We have the several examples here. Then if you have 3 bonding pair and 1 lone pair. We call it a trigonal pyramidal. Ammonia, NH3, is a very good example of that. And then we have another example where it is bent or V-shaped. Once again, if you disregard the lone pairs, you can see right here it's a bent or V-shaped. Then we have 5 electron groups as well as 6 electron groups. We will look at them as well. So 5 electron groups, it's a trigonal bipyramidal. So you have right at the center, you have a trigonal planar base, you can or midsection, and then it can form a pyramid up at the top as well as down at the bottom. That's why it's called trigonal bipyramidal, because it can form 2 pyramids. A very good example would be phosphorus pentafluoride, PF5. Then we have a seesaw shape when you have 1 lone pair of electrons here and then 4 bonding pairs. It looks like a seesaw. You just have to like turn it 90 degrees to in order to visualize the seesaw. Then you have T-shaped. Once again, as you can clearly see, there are 2 lone pairs and then 3 bonding pairs around the central atom, so it looks like a T. That's why it's called a T-shape. And then we have linear, in which there are 3 different lone pairs and 2 bonding pairs around the central atom. Last, we'll look at 6 electron groups quickly. So we have the octahedral shape. So you have central atom and then 6 side atoms around it, and these are all bonding pairs in this picture. For example, sulfur hexafluoride SF6 is a very good example of octahedral shape. Then we have another example where you have 4 bonding pairs and 1 lone pair down here. It's called square pyramidal because it has a square base for the molecular shape, and then you can form a pyramid on the square base, so it's square pyramidal. And then you have this case, in this case, the square planar molecular shape. Remember, all of them have the same electronic shape of octahedral, but molecular shape for each of them is different because we are considering only the bonding pairs of electrons when we are describing the molecular shapes. Next, we will look at trends in electronegativity. We discussed this before. I'm just going to do a quick review of this. Trends in electronegativity is how the electronegativity or capability of atoms to attract electrons towards itself changes across a period or down a column. So across a period, we know that the electronegativity increases because every time you're adding 1 proton, you're adding 1 electron as well, but remember you're adding the electron to the same shell. So the positive charge increases and attracts the electrons more and more strongly as you go across. But as you go down the group, you're increasing the number of protons, but at the same time, you're increasing electrons as well as adding a shell, extra shell, and that's why the size, atomic size increases, which causes the electronegativity to actually go down. So basically, non-metals tend to be more electronegative than metals, and that's what we see across a period as well as down the column. So this is just the Pauling scale that we use, electronegative scale, and you can see numerical values assigned for the atoms in terms of the electronegativity. Now, what we're gonna look at is how the electronegativity of atoms can explain bond polarity. So electronegativity, as we have already said, is the capability of atoms to attract electrons towards itself, right? So if you have 2 atoms with different electronegativity, basically, so if you have one with lower electronegativity, we give it a partial positive charge, so it's more positive compared to the one that actually attracts electrons more, we give it a delta negative partial charge. So obviously, the delta negative would actually attract the electrons more towards itself, and that's why in order to represent that bond polarity, we use this arrow sign, and you can see the end of this arrow, it looks like a plus. So that's kind of actually a reminder that hydrogen is partially positive while fluorine is electronegative, and that's why we always describe the arrow or describe the electronegativity difference or the bond polarity by starting from partially positive towards partially negative. So in this case, in hydrogen fluoride, this is a polar molecule. It's a polar bond, as well as it's a polar molecule because there is electronegativity difference between them. So you can think of it as a vector force. So in elementary physics, you have probably encountered and saw that vector forces basically have directions. So it's not a scalar quantity, it's a vector quantity. So it basically gives you directions, and you can actually combine different vector forces to find out the resultant vector force, and that's how we determine molecular polarity, as we will see in the next few slides. So we talked about polar bonds. Now, how do polar bonds uh, um, explain polarity of molecules, or whether a molecule is going to be polar or not? So whether a molecule is polar depends on two different factors. One is the molecular shape, that is determined by Vesper theory, as we saw earlier, as well as the bond polarity, as well as what kind of bonds are present in that molecule. Well, we'll see a couple of examples in the next few slides. So the polarity of a molecule is measured using net dipole moment, which is a vector force, and we will see how bond polarities, we can combine them just like we can combine vector forces, and then we can determine the resultant vector to determine whether it has net dipole moment or not. Now, the rule of thumb is a molecule is polar if it contains one or more polar bonds. First of all, it has to have polar bonds, and it also has to have the individual polar bonds. They need not cancel. So if the polar bonds cancel each other out, then the molecule is not going to be polar. The polar bonds that are in a molecule, if they do not cancel each other out, if they have a resultant dipole moment, and that would actually make the molecule polar. So we will look at the example of CO2. In case of CO2, carbon is more electropositive or less electronegative compared to oxygen. So once again, you can see the arrow. This part it looks like a positive sign. So carbon is more electropositive, or carbon is less electronegative, and oxygen is more electronegative. So we will have a polar bond or dipole moment in this direction, CO, and another dipole moment in the exact opposite direction. So CO dipole moment to the right and CO dipole moment to the left, they cancel each other out. So even though this molecule, carbon dioxide, has a bond polarity or polar bonds, CO polar bonds, two CO polar bonds, but since they are exactly in opposite direction, these two polar bonds, or these two dipole moments, cancel each other out, and the net dipole moment is zero. And that's why carbon dioxide is a non-polar molecule. Let's look at another example. In this case, once again, we have so this is a 4-electron group system. As you can see, you have oxygen, it has two lone pairs, and then once again you have two polar bonds, OH and OH. So as you can see, the direction of the polar bond. Now in this case, the polar bonds do not cancel. The dipole moments of HO and HO, they do not cancel. In fact, they will have a net dipole moment uh, uh, in the top direction. So in this direction, there's a net dipole moment right here, and that is because if you add these two vectors, this one and this one, it will have a net dipole moment in the top direction, and which makes water a polar molecule. So next, we're going to look at some more examples. So molecules with the same shape, they may have different polarities. And that is because if you have a central atom and if you have all the side atoms the same kind, then obviously those polar bonds, even if they are polar bonds, those bond polarities, they will cancel each other out. But if you just replace one of those side atoms with a different atom, then we will see that the molecule suddenly becomes polar. So for example, in this case, carbon tetrachloride. So in case of carbon tetrachloride, you have central atom carbon, and then chlorine, they're more electronegative. So we have this wedge, so that means the chlorine is taken out of the screen, and then the dashed line means chlorine is going behind the screen, and then you have solid black line means carbon-chlorine bond is on the screen. In this particular case, these three right here, this one, and this one, these three base vectors will produce a resultant vector which is in this direction right here. sorry, I'm trying to draw it as smoothly as possible. So this direction right here, it will create a resultant in the green direction, and that will be exactly equal to a CCl dipole moment, or CCl force, vector force up at the top. So which means that these two will cancel each other out. The green line and the black line right here, will cancel each other out, which will make the molecule nonpolar. So carbon tetrachloride is actually a nonpolar molecule. But let's look at a similar molecule with the same structure. So you have, in this case, carbon attached to 3 chlorine and then 1 hydrogen. In this case, once again, you'll have the resultant right here, right down here. So this resultant force, once again, or this resultant dipole moment, is going to be equal to a CCl bond. The polarity is going to be, the dipole moment is going to be equal to a CCl bond, but that CCl is not going to be equal to the CH right here, the CH that you can see right here. It's not going to be equal to that, because CCl bond polarity and CH bond polarity, they're not the same. As a result, this molecule is going to be a polar molecule, because the polarities don't cancel each other out. So I'm going to erase this real quick before I move on to the next slide. So in this case, we will look at an example of cis-trans system. In this case, once again, as you know, that cis means, in this particular case, we have 2 carbon at the center, and then 2 chlorine on the same side. And then if you have 2 chlorine in opposite directions, we call it trans, and on the same side, we call it cis. So once again, if you look at this, you have CCl bond right here. We have 2 different CCl polar bonds, and the resultant polar bond is going to be down here, which will make this molecule, the molecule on the left, a polar molecule. On the other hand, we have this CCl bond right here and this CCl bond right here. They're exactly the same, and they will cancel each other out. They're pointing in exactly opposite direction, vectors that can be, like moved around in this case, you can align them, and they will exactly cancel each other out. As a result, the left cis molecule is a polar molecule because it has a net dipole moment, while the molecule to the right is a nonpolar molecule because the bond polarities cancel each other out. As a result, and this is very important because the cis and trans molecule, even though they have similar structures, they have very different physical properties. One has a higher boiling point compared to the other. The polar molecule has, which is the cis isomer, has a higher boiling point than the nonpolar molecule. It is because of the stronger intermolecular attraction. So we will wrap this up with a couple of examples, in-class examples that we will do. So ammonia, in this case, if you draw ammonia, so you will see that ammonia has NH3, and these 3 bonds, due to the electronegativity difference between N and H, they form polar bonds, and it has a net resultant bond polarity or net dipole moment in this direction. Let me use the green instead of the red. So the net dipole moment is going to be in this direction. So that makes ammonia a polar molecule. On the other hand, if you look at boron trifluoride has a very symmetric shape. As a result, if you have the BF, these two actually, due to the polarity of these two BF bonds, we have a resultant force in this direction, and this dipole moment is exactly equal to the dipole moment that you can see. They're both represented in blue, and they cancel each other out, making this molecule nonpolar. Last example that we're going to look at is carbonyl sulfide. In this case, carbon and oxygen. Carbon is the positive, electropositive, or less electronegative, while oxygen is more electronegative. So in this case, you can see that oxygen is the most electronegative, then carbon is the second electronegative, and then sulfur is the least electronegative. As a result, you can, if you draw the bonds or draw the dipole moments, you'll see it will have a net or resultant dipole moment in this direction, and that will make the molecule polar. So that's basically it. That is molecular polarity in a nutshell. And I hope you guys understood, the lecture slides. And if you don't, if you have more questions, you can always come to my office hours to ask more questions. We are kind of pressed for time, so we will end it right here. Thank you very much.